start right into the concept for tonight. What we're going to be talking about, let's go ahead and, is 13.3, which is the start, sort of the introduction to the definite integral. We will actually do stuff with the definite integral next Tuesday, where we'll actually calculate with it. Tonight's lesson is going to be about something called Riemann Sums. So we're going to look at a graph, and what we're going to see is we're going to graphically, geometrically find the area under that curve, which will get us a feel for what the integral, the definite integral, actually finds. Okay. So tonight's lesson in itself is not really important because you're not going to use this again really for anything, but this was how the concepts were developed. So if you can follow along a little bit, you'll be fine. I've also got an app on my calculator which I can download to yours if you have a TI 83 or 84 that will actually do all of this for you, and it shows you the nice pictures, and I'll demonstrate that with the camera here. So you'll be able to do it with this. The main thing is that you follow along with the concepts, and basically all you have to know is how to get the area of a rectangle. How do you get the area of a rectangle? Base times height. Cool, that's all there is to it. So that's really what's going to happen in this lesson. So we're going to start with, they give us a function, and this is a function that we have a deep sea ocean oil rig has suffered a catastrophic failure. I didn't read that part. This is kind of sad. The oil is leaking from the ocean floor. Wow, that's terrible. I thought it was they were pumping it out or something. I didn't like sometimes you just have to. Anyway, that's what's happening. They come up with an equation that how many barrels per day is getting out of there, and I guess it takes 20 days to maybe hopefully get it fixed. But what we want to see is what was the total oil that fell into the sea over those 20 days. So the first thing we could do is, assuming that this equation works, and that's a lot what we have to do is assume, we could graph the equation. Okay, so here's the equation that they gave us, and since this is the rate, right, 1,000 barrels per day, right? Remember, whenever you see that word per, that's a rate. So this is a rate that's coming out. And we can see if you put in 0 for t, initially it's 60,000 barrels a day. But it's got a negative here, so maybe it's going to go down, and when we graph it, it is. But it's a derivative, right? It's a derivative of something. And so eventually, on Tuesday, we'll see we could integrate this, and then we can do it all, use our tools and everything. But what we're going to do tonight is try to approximate it with just saying, well, let's find the area under the curve. Because that's what's happening is if we have a rate, we are calculating sort of the accumulation of stuff. Okay. So the area under this curve, one way we could do it is we could say, okay, what if it was actually, I've got to get my, let me get my tools. So what they're going to start off with is say, okay, let's just take the average. What if it was 60,000 barrels a day average for 20 days? And we take our 60,000 times 20, and that's going to give us, that's 12 with 2 zeros behind it. And those are thousands of barrels. Over 20 days. And what we did is we came up with just one big rectangle, and we took 20 as its base, 60 as its height, We multiplied those and we got the area. Have we over or underestimated the amount of oil? A big overestimate, right? We're including all of this that is actually above the curve. It didn't really happen. So, but that's a very rough estimate we could get. You know, if we, the day one, we see this coming out here. Well, if it doesn't slow down, it's going to be 1,200,000 barrels in 20 days. Okay. What we're going to do is we're going to work on how could we get this more accurate. So that's what we just did. There's a sort of a nice little drawing of it, right? It's the whole rectangle. How could we get it more accurate so we're not overestimating so much? There we go. Make more rectangles, right? So what we would do is, okay, we'll take this one, but about halfway down we could take a rectangle and do this. And that would be a better estimate because this one would only go to here. So we would cut off some of that over, right? Good choice. And that's what they do. So let's cut it in half and let's cut it into two intervals. So if it's 20 long, if we're going to do two rectangles, each would be 10 long, right? 0 to 10 and then 10 to 20. And so now the base of each of these rectangles is 10. And the first one starts at 60, notice, and this is what we're going to call a left hand because we're starting with the left side, a left-hand Riemann sum. So this rectangle here is going to be 60 times 10, 600, right? And this rectangle over here only comes up to, looks like 30, right? Because it starts here lower on the curve. So that's going to be 30 times 10. And so now we've got an estimate for 600 plus 300 for the two rectangles. So we're down to 900. We went from 1,200 to 900. Much better estimate because we got rid of the stuff that really didn't happen. But do we still have an overestimate? Yes. So how can we make it better? Yeah, you can do it. If it gets better with 2, how about with 3 or 4? 4 is what they did, right? Because nice and even. You've got 20 divided into 4 regions. Each is 5, a width of 5 as we see. And notice they're taking the function values at the left side on the graph, and we're getting smaller and smaller rectangles. So again, each of these has a width of 5. So the first one is 60 times 5. And then we're going to add the next rectangle, which will be, looks like 40 times 5. And then the next one, which is, what is that? Is that about 30? Yeah, I think, because we did it last time too, right? So that'd be 30 times 5. And then this one looks like 20 times 5. So notice we've divided it into 4 regions. We have 4 areas. Now, one of the things that's going to be cool that you'll see when we actually go to calculate this is that we keep the bases are all going to be the same because we're taking that area, dividing it evenly into 4 regions, 5 regions, whatever. So these will all be the same. So another way you could do this is just add all the numbers together so you don't have to keep multiplying. And then multiply by 5 at the end. It's a little bit easier to calculate in our heads, right? Either way works, but instead of multiplying each by 5, just add them. That's 100 plus 130, 150. So now we've got a total of 150 times each having a width of 5. So this will give us, again, a better estimate. And that's what? 750? 750. Still a little sharp tonight. I don't know how long that will last, but you know me, my arithmetic goes on me. So better, but how could we get better still? Okay, yeah, you got this. So here's the calculations. Actually, I guess it ended up being 740. What did I do? I must have read one of them wrong. They've got 300. So that's the first one. they got 210. So this maybe is like a little bit more than 400. Must be 410, 41. Anyway, we do the best we can with estimating, right? So they came up with 740. I couldn't get that close. Again, as we see, the more and more intervals we use, we're going to get smaller and smaller, or the width goes down, and we're coming to the function more often, and there's less overlap. There's less overestimation. And then we get to 675. And if we do it that many times, why not do it so many times, right? I don't know. They did 80 subdivisions. Again, that's when we go to the calculator or a computer or something. We get down to 619. And then if we do it exactly, which we will learn how to do that on Tuesday, the exact value is actually 613. But you see, we got to a really good estimate by doing this Riemann sum thing. Okay, and what are we doing? We are getting the area under a particular part of the curve. We're using the function itself, the function values, and then we're using the width. And what we see is we can do a left hand like we've been doing here. I'm also going to show you there's another thing. We could do a right hand where we started to the right of the interval, and that will give us an underestimate, as we'll see. And then to get really accurate, if you take the left hand and the right hand and you average them, you'll get almost exactly what you need. This was the way they developed this thing called the integral. Okay, this is how they came to understand it. This is the way they sort of proved it. This is what we're getting, and then when they got their math techniques good enough, they were actually able to find the area under any curve. Okay, so let's see, where should I go from here? So just let me show you what it would look like with the right hand. So let me go with, let's see, that would be 1, 2, 3, 4, 5, 6, 7, 8. Let me do it with 8 regions. A right hand means we're going to take this first region here, this width here. We're going to make a rectangle, but we're not going to start with the 60 and go over and overestimate. We're going to start with this endpoint and go backwards. So that's a right hand. Notice that we're lining up the rectangle with the right hand side. And this is going to give us an underestimate. And this is what you sort of do if you don't want to work too much. You could still do this with 8 intervals and get pretty accurate. If you do it with a left hand and a right hand and then average it, you'll get almost exactly, rather than having to go to 80 subintervals, which is a lot of calculations, right? So that's this area here. And then this one would, again, it gets harder to estimate because, right, this is not exactly on a line, but this is what our intervals start looking like. And part of what the homework you're going to do is they give you graphs, and you're going to do exactly this. You're going to subdivide it into that many pieces and then kind of estimate it with the intervals. So the one calculation we have is it's 20 long, right? And we want 8. We want to divide it, in this case, in 8 pieces. So 20 divided by 8 will tell us that each of them would be 2.5 wide. Okay. When we did it in forward, each of them would be 5 wide. So that's one of the calculations we'll do to see how wide it is. And then again, what we're doing is we're just reading this function value. So the function value at 2.5 plus the function value at 5. And the nice thing is, since we do actually have that function, we could put it in our graphing calculator, look at the table of values, and come up with these pretty easily. And then we got what, f of 7.5 plus f of 10, and so forth. And then we're going to multiply this whole thing times what? How wide is this? It's 2.5. That's the width. Each of these is 2.5 in width, so we multiply each of them by 2.5. But I like to think of it, just add them all together, so you're adding all the different heights, multiply by the width, because they're all going to be the same. Okay, so that's all it is. That's all we're doing. And anyone know why they call it a Riemann sum? some guy named Riemann invented it, or at least got credit for inventing it. I was reading, there's like one guy, and maybe it was Riemann, was one of these guys in calculus who was just rich and bought it off of other people. He had other people doing his work and was basically paying him slave labor, but he got to take all the credit. And he had like a legal contract. Since I pay you, I own it. My name's going on it. I can't remember if it was Riemann, but it was one guy. I kind of lost faith when I learned about that lesson. So, again, this is just kind of wordiness. I leave it in there, but the volume is the area under the curve. We divide it in, and we're just doing rectangles, okay? Because we don't have any geometry that really gives us for a smooth curve. Although we will get calculus techniques of finding the antiderivative, and then we just plug in 2 points, and we actually get it exactly. Yes?
So when you're approximating, do you have to approximate it to a specific time? So if it did it 68,000 times, do you have to specify that this is the amount at every minute?
Yeah. Yeah. So however many intervals you're going, you've got to get a function value for that, and then you multiply it by the width. So yes, the more intervals, the more calculations you have, if I hear you right. And again, I put this here just so we could talk a little bit about notation. Again, don't let it scare you. We're not going to really use it all that much, but each interval, they start labeling them x1 all the way to, the endpoint that we were working with, we call that x0, or the starting point. That was when it went up to 60, right? And then x1 would be the next interval, x2, x3, all the way to xn. So this would be the last interval. And so we end up with however many intervals in intervals. And again, we did one with 8, we did one with 4, did one with 2. So the more we do, the more accurate we're going to get. So we start at A, and these are all just divisions of it until we get to some point B. And the more we have, again, the more we're going to get. And so one calculation you can use is you take the endpoint minus the starting point, and that'll give you the width of the whole thing. In our case, it was 20 minus 0, so it was 20. And then we divide by however many units it says to divide it into. Okay. So again, just it's kind of a little bit of overkill. And you'll see this thing called delta x. Delta is the change in x. So that's the width of each of the rectangles. Okay. So when you see this, that's what it is. And it's going to be, that width is going to be a calculation of the endpoint minus the starting point divided by however many rectangles they tell us to use. Okay. What I'm going to do is, let me turn this thing on. I'm going to show you how this calculator it's got a program called Riemann. I've also got, I'll set it up in Canvas. There's a page I had from last time I taught this, where if you know how to do it, you can download. It's got a little program you can download to your computer and then upload it to your own calculator. But if you got your calculator with you, I've also got the cable. We can just download it tonight. It takes about 3 or 4 seconds. But let me show you. What do I do here? Let's go to the document camera. Plug this. And I'm sorry for those watching the video, you won't be able to see this because I don't know how to switch the document camera to the video, but maybe I'll make one of these later. So let's just turn it on. It's focusing pretty good. So what I'm going to do is I'm going to go to Program, and I've got only one program because this is, Riemann. This is what I would download to you. You would do the same thing. You would go to Program. If you've got this, great. I'm going to hit Enter, and it says Program Riemann. So it's getting ready to run it right now. I hit it again, and it's actually going to Well, Riemann. Oh, I hit enter again. Okay, still going to work. Okay, so I don't know what that was. Settings. So first thing I have to do is I have to put the function in. You have to have the program.
Oh, okay, well, how do
Yeah.
we get further on?
You wait till after I finish, and then I'll download it for you. Yeah, you can't do it now, but we'll do it. Yeah, but this can do all your homework once you have it. Okay, so now where am I? I need that function. So let me back up. What was the function? So it was, I'm going to do exactly what we just did. It's 0.08 x squared. Then it was minus 4x plus 60. And the cool thing is it's going to show us a graph. It's going to show us all the little boxes. It's going to do all the calculations that we needed to do. And then, so now that it's there, I've entered it. Oh, there's a press I for info. I've never done that, but you could give it a try. It probably gives you some info. So then it says, okay, this is your equation. What's the lower bound? So on our graph, we wanted to go from day 0, right, to the upper bound of 20. That's what we were working. So we put in the lower bound is 0. In the homework, they'll give you that. Do it over this interval, the lower bound to the upper bound. So we're always given this. Now it asks for the upper bound, so then I'll put 20. I hit enter. Now this is where how many partitions do we want to put? And again, the question will tell you. Anyone have a suggestion? 12. Why not? We didn't do that, right? Let's go ahead and do 12. And then I hit enter. And nothing's happening. It draws it. And this looks familiar, right? That's kind of the graph we were looking at. Starting from 0, and it knows we're going out to 20, so it's got everything. It hasn't found it. It does put the boundary here, so it makes a nice fitting graph, and then we have to hit enter. This is where it's going to ask us, do you want a left sum or a right sum? Or do you want a midpoint sum? We didn't even talk about that, but the midpoint is even more accurate because you put the midpoint in, so it's a little over and a little under. But so it can do all of this, and again, the question when you're doing your homework will tell you whether they want a left or a right. We were doing left-hand ones, right, on the slides. Why don't we do a right-hand one and see what that looks like? So I'll do a number 3. Actually, I'll just arrow down. And this is really cool. I'm amazed by little things, but it actually draws them. I don't know how it does that. Actually, I've looked at some fancy programming that's been done. So it's done the right sum for us. And notice it's come up with 574. If we count this, we would see there's 12 little boxes, little rectangles, because that's what we told it to do. And it gets us this estimate. And notice it's less than those other estimates that we got because it's underestimating because of the right side. If we did the left side, but it's nice and easy to do. And the thing I like about this is actually it draws a picture so I can see what it's doing. Doesn't that make sense now? I mean, you kind of see a Riemann Sum. Okay, I asked for 12. There's 12. And what this is the area of all these little rectangles. Again, I could figure it out what this is because I could take 20 divided by 12. Maybe not in my head, but 20 divided by 12. Who could? It's less than 2. 1 point something. Maybe 1.8. It's, yeah. 1 point, thank you. 1.6. So it's got a width of 1.6, and then I could actually go in and find what those values are on the right side. So this would be 0, this would be 1.6, and this we keep adding 1.6, and you could do those. It would be kind of complicated, right? But you could do it. But it's nice that this did it for us. And on the homework, all I'd have to do, oops, well, it went away, is enter that number. But so it's going to do it.
So the partition, should you choose a larger number?
Well, you choose what the homework tells you, and they keep it fairly small. There's usually 5 or maybe 8. Because you get too many, yes, you will get more. I think there used to be ones where they would have you do more and more and get it more and more accurate, but they don't know that you have this little secret tool. And so they're trying to make it easy on you, so because otherwise, you know, we'd have to do 12 calculations here, right? Not too bad, but what I'll show you, what's kind of cool, I'm going to quit this, is when I go to y equals, this program actually puts it in my graphing part of the calculator. It's actually using, it's like it took control of the calculator. It's a little scary, but you know, it's AI stuff. But that's what it did. But now what I could do, if I needed to check it, is I could go to my table, right? Maybe I'll set up my table. I'm going to have it start at 0, and it's changing by 1.6, right? 1.6, we figured that out, 20 divided by 12. 1.6, I'm going to have the table start at 0, change by 1.6. I'm going to put it onto auto. Why doesn't, oh, the one thing it didn't do, notice the equal sign is not darked in, so when I exit it, it sort of turns it off. I'm going to turn it back on. That's why it's not showing me anything. I forget about these things. So now when I go back to my table, it gives me the y values for each place that I need. And again, this first one would be the left-hand side. Since we're doing right-hand, I would use this number first, so 53.8 plus 48 point, you know, so I would just add the first 12 of these together and then multiply by 1.6, and I would get exactly what they got. Okay, so here's another way. So even if you didn't have this program, it's not incredibly taxing to do this if you're using a graphing calculator. You can get these values. I wouldn't plug these in by hand and calculate each one, but this table, you get your table set up. And your starting point is the right-hand side. However wide it is, that's your change. So in your table setup, this is the right-hand side. That's the width of each one. And you put your table on auto, and that will give you all the values you need. And then you just keep going until you get to the end. And again, for us, since we ended up doing right-hand sides, it will end at 20. Should have ended at 20. Let me do something. 20 divided by 12. Oh, it's 1.6666. It's a terrible thing to choose 12 because it's not. It's a repeating decimal, so we can't do it exactly. So we wouldn't use 12. So we would use something that would give us a better. But you see how we could, right? That's why it didn't get us all the way to the end. So we try to get something that would go in at least evenly. It's okay to have a decimal, but we don't want a repeating decimal. So, and the homework knows that, and they won't have you do that. We'll take a quick look. So is that convinced anybody? Anybody want this program? Yeah. Okay. We'll pull out the cable. Just come see me. We're almost done because that's pretty much. I mean, conceptually we're done. When did we start? It's only a half hour. So what we're going to do is look at another example and maybe detail it, but knowing how to do the calculation, we've pretty much done it. Okay. So let's see. So that's that. I have to get back here, kind of walk through it. And again, they just detail it through, going through, okay, this is 4 sides, so you can find each function value, multiply by the width. You do all that, add them all together. That's how they're doing it for n equals 4. If you can understand n equals 4, you can do it with larger numbers, n equals 8, n equals 12 if you want. But it's just length times width, right? Length times width each time. And since the width is always the same, we could just move it to the end and just add all the heights. And that's what they do. So they just f of 0, f of 5, f of 10. So they're adding the function values all times the widths, and that's how they're getting it. And down here is just some the notation. It's called sigma notation because that's a Greek letter sigma. It's used for the sum, and it just really means that I think there's a problem with this. It should have this should be like f of x sub k. So you're going to take each one, f of x naught, f of x1, each times the change in x. So it's just a shorthand notation. But if you're a math major, we would delve into that because you would use it a lot. But all we're wanting for this is the concept, and then we're quickly not going to use it much. In fact, I don't even know if they put it on the test. I wouldn't put it on the test if it were me. I'll look ahead to see if it is, but they might have one. So that's why, again, it's good to have. The only thing, it only works on a TI 84 or 83. Even if you have the older 83, it still works on it. It's an older program. But anyway, so this is just more of the same, a lot of notation, and basically just saying however many intervals you're going to use, take the function value times the width, function value times the width, however many intervals you do. If you do 12, that's it. If you do 80, that's it. And then you add them all together, and that gives you the area under the curve. Okay, and again, however many you use, you take the interval, the n minus the beginning, that's your width, divided by n, that gives you the width of each of the individual rectangles. Okay, so here's another example, more generalized. We can do it with any curve. We don't have to start at 0. We could start anywhere, but we start somewhere at one end. So we are at interval A to B. This is a left hand, right? And so some of these are actually underestimating, and then others are overestimating. So sometimes these you actually come up pretty accurate because you've underestimated on one side and you overestimate on the other, and they add up, and you're pretty accurate. Sometimes. We don't always know. And again, we're going to get a method where we'll get it exactly. But all it is figuring out the width of each rectangle, and those will all be the same. Incidentally, what happens when we do this integration of the function, which is what we're going to do, delta x becomes dx. So I kind of skirted that because there's some what is dx? Well, it's really that change in x. It's the width of the rectangle. But we make it so small, it's really, I didn't want to tell you, I didn't really want to talk what it is because we make it infinitesimally small so that it's perfect, right? So it's not really a width, but that's what it came from. So this, remember, we're just taking f of x times the change in x, and we're adding all those together. That's what the sigma means. That's what this integration means, is we're summing all the parts of the area. But we're doing it so smoothly and continuously that we've got rectangles that really have no width. They're only height. But there's so many of them, they fill up. Okay, so this is where we're going, and this is where it came from. So conceptually, this idea of having a rectangle, we just get them smaller and smaller, more and more of them, we'll get accurate. And then the math theory says, oh, we could just go and do what we've been doing and getting that antiderivative, and then look at it from A to B, and we're done. Okay. So just talking about the Riemann sum again. Again, if we had only one box, it was 60 times 20, and it was 1200, right? We put two boxes, and when we had two boxes with the width of 10 each, we got it down to 880. 4 boxes, we got it down to 440. 8 boxes, we got it to 675. We went with a right hand with 12 boxes, and what we had like 574. So these are all still estimates, but we got sort of closer and closer. So this part of this thing is just talking about how, basically doing what we just did, is how do we do this? And I'm gonna do it multiple ways. So let's do this sort of pretending we don't have the calculator, and then I'll do it with the calculator for those that have it. So this is much like a homework problem. Compute the left Riemann sum for this function over the interval -1 to 1 using n equals 5 subdivisions. So they kind of get us started. So how wide is this interval? Well, we're going from 1 is the left endpoint. We're going to subtract -1, which is the starting point, right? So it's the ending point minus the starting point. That's what that is. And then we divide that by however many intervals we're going to have. So this ends up being 1 plus 1, which is 2 2/5. So each of our rectangles will be 0.4. Okay, that's our width. And so you could think we're going to start at -1. You add 0.4, so we'll get to -0.6. Add 0.4, we get to -0.2. Add to 0.4, you keep going, right? So I'm going to show you, and again, I would not do this by hand, although you know it's not too bad. You can plug in for x squared and square it and then add 1, right? That's what we're doing each time. But what we want to do is we're going to enter this as a function, and then I'm going to go into my table, and let me do this. I think I can do both sort of at the same time. Let's come back here. Camera. So I go to my y equals. This is all, if you want to do it manually, we'll do it with the program. You'll see it's even quicker. We just put in x squared plus 1. So that's my function. I go to my table set. Where did I want my table to start? The left-hand side was -1, right? So I had to, that's what they gave me. And then I calculated the width of each rectangle to be 0.4. So that's what I want my delta table. That's really, could just be delta x, right? 0.4. Now watch how cool this is. I go second table. It's starting at -1. And just like they did it, it goes to -0.6. But I don't really have to calculate it because this will do it for me. And I keep going until I get to 1. Now, I don't want to include 1 because, let's see, how many intervals do I have? 1, 2, 3, 4, 5. Notice this is my last one. So when I'm doing left-hand sides, I start at the back side, the left side, and I go 5, but I don't use, because this one at 1 is going from 1 to 1.4. It's outside of our interval, right? Now, if I do right-hand side, I would basically use the same table, but I wouldn't start at -1 because I would start at 0.6. So this would be the right-hand side, and I'd use 1, 2, 3, 4, 5. I would use that for my estimate. Okay, so it doesn't make sense of, I could do this all by hand. It's going to be using the same table. If I do the left-hand side, I start at the left end of it, and I end just short of the right side, right, the one before. If I'm doing the right side, I start at the second interval, or the second little division, this point, I would start at -0.6, and I keep going all the way to the end. Okay, because that would be the left. Because these are, remember, these are just function values. So at that value, x has, the function has that value. So we would add all these together. And let me see if I can, they wanted the left Riemann sum. I'm going to write it down while it's up there. Let's see. So we've got 2, we've got 1.36, we've got 1.04, we've got 1.04, that happened twice, and then the last one will be 1.36. And then, I guess I could have left that down, back to here. So I just now need to add those together and then multiply by what? The width, right? The width was 0.4. That's what I calculated up here. So I've got the heights. These are basically the heights of each of the rectangles. And again, that's why if you do it this way, just kind of add them all together. 2 plus 1.36 plus 1.36 1.04 plus 1.04 plus 1.36. I come up with 6.8. We multiply that by 0.4 times 0.4, and I come up with 2.72. And that's the area under the curve. Okay. Now, there was a little bit of abstraction, right? I didn't draw a graph. I don't really see that this is area under the curve. That's why I like using the app, because it's going to draw that for me, and we'll see. Okay. Width of the subdivisions. Okay, there. So here we've got the picture of what we're doing. So here's the graph. 2, 3, 4, 5. There's 5 subdivisions. Some are overestimating, a little bit over there. Some are underestimating. So we could probably feel, you know, if you put the overs with the unders, it's probably a pretty good estimate, right? And then they did exactly what we said. The function value at -1, -0.6, they did all of these. They added them all together. Let's see. They went to their table, just like we did. So, and you know, with these things, know how to set up your table to be what you want it to be, the table change. So it will give it to you just like this. All you have to do is write it down and then add it separately. But no, it's 2.72. That's all you have to do. You could do that, so we don't need the program, but if you have the program, we go to Program, Riemann is selected, so I just hit Enter to execute it, Enter again, and then this time it just went right to Settings. It asked for the function. What was it? X squared plus 1? Okay, thanks. X squared plus, no, plus 1, not 2. I think it was, right? Do you want to enable dictation? Not now. Yeah, X squared plus 1. As for the lower bound, remember they told us -1. Upper bound they told us was 1. Partitions they told us was 5. So thinks a little bit, draws the graph for us. It knows the boundaries. It's going to show a little line here that A equals -1, B equals +1. So the picture's there for us now with a clearer understanding. We hit Enter. And we need to do the left hand. If they ask for the right hand, we could do that just as easily. But they asked for the left hand, so we're going to do that. We hit Enter, and it shows that. So we see pretty much the graph, and it's 2.72. It just did it all for us. But if you do use this, I want you to take the time to look at the graph, and so that you understand what it did. Right? This 2.2 came from left hand boxes that are each 0.4 and at the different heights. You know, and the homework's not too much, so you could, you know, maybe do it both ways, but however you want to do it. Okay, but this I like this because I can see what the result is. I see the graph. I guess I don't see the calculations, but I know what it's doing. You know, so maybe I do a few. Maybe I just do one of them with the calculations using the table. Okay. So that's pretty much it. We gotta have enough time to load everything up for people, right? Oh, really? Looks like we're done. Can't go anywhere. No, we don't need to keep it. That's right. Because there was actually a whole nother section on definite integrals, but we're not doing that till next Tuesday. So we're going to pick it up then. This is all that's on the homework. So let me just show you real briefly, since I have our course open. So 13.3. And I'll just show you, we'll just kind of scan through what's on the, so it's 7 questions. They're going to ask you to do a Riemann sum here. They give you an equation. It's actually, it's a linear equation. They give you the interval from -1 to 1 with 4 intervals, or four rectangles. So this one actually won't be too hard if you wanted to do it by hand. But again, this the calculator will handle it too. Another one, a left Riemann sum. Another one with the left Riemann sum. So they kind of stick, again, different equations. So the calculator will handle it, or graph it and use the tables, right? Here's a left Riemann sum with an exponential. Again, it all handles, it's all the same thing. You just graph it, divide the graph. This is going from 0 to 10, divide it into 5 intervals. So 0 to 10 divided by 5, so each is going to be a width of 2. And then these are the ones, then there's 3 of them that are like this, where they just give you the graph. They tell you to divide it into 4, so we're going from 0 to 40. If you divide 0 to 40 into 4 rectangles, how wide is each rectangle? 10. So it'll be, a width of 10. So if we're doing a left interval, it's 25 times 10 will be this rectangle. So you could just kind of do it graphically. And again, we're going to have to estimate, right? Because if you come here, what's this here, right? That's 5, that's 15, that's 10. I don't know, it's 6 or 7, maybe 7. Not quite half. So do the best you can with the estimates. I believe there's some problems with this. Let me know if it's not doing it, but just write down your numbers, and if it says you're wrong, you might just try it with, if you tried 7, maybe try 8. But if it's putting in, some of these problems I figured out, it was actually putting in something like 7.5. How would you know that's 7.5? Only if you had the function. So basically we just need to estimate, and then we come out, so that's 10. Here's another one here. This one's pretty good. It looks like set on at 5, so I got to 10. And then this one, again, I'm going to have to estimate. Maybe it's 8. And then I go to the end. But if it was actually 7.5 and I had 8, I might not match their answers, but I want you just to be doing it right. So kind of go through these. And they don't give the equation, so there's no way to find what exactly those are. We're just doing the best we can to estimate, okay? So hopefully it's forgiving. Like this one, it looks like it might be a little bit of trouble going from 1 to 9, right? So 1 is here, 9 is here. And again, you're going to estimate it 4 intervals and left Riemann sums. Actually, maybe, did they ever get into right Riemann sums? They don't. Maybe I could have just skipped that. But we could do a right Riemann sum. But the main thing they want you to see is what we're doing is we're approximating the area under a curve with just rectangles. Okay? And then what we're going to do is we're going to take it and just say, basically, there's a way where we can get an infinite number of rectangles, and that's what we've been doing with the integration. We've been putting a plus c. We won't need to do that anymore. We'll actually just integrate, and then we'll plug in the end point and the front point and subtract the two, and we get it. Okay, so there's an easier way to do it, but the homework is really just about getting some practice with it. And again, the first 4 you can do with, you just entered this in and you'll be done in just a few minutes, but you might want to take some time just to, at least with one of them, try it by hand. Whew. Is that it? I think it's it. So, any questions? Did any of it make sense? A little bit? Okay. A little bit more than before? Great. And so yeah, we'll end it there. If you